most familiar ones are polynomials of degree 2 and degree 1. Linear function, quadratic function, or cubic function, they are the nicest. But if you look at these equations here, the equations are very bizarre and odd and the weird graphs out there. There are a lot of weird graphs out there. Okay, and when you look at the equations, you cannot separate the x and the y, and you cannot write y equals fx or x equals g of y. You cannot write it that way. And so we cannot apply the usual definition of a differentiation. That is, we cannot take the derivative. So for these, we are going to apply what we call implicit differentiation. All right, so to practice, so example 1, A, B, C, we are not ready to work on those graphs yet, those equations yet. So here, over there in example 1, I just gave you some equations which cannot be solved for x, which cannot be solved for y in terms of x, nor can it solve for x in terms of y. Either way, you can't do it. As you can see, it's so very messy, and we cannot do it, okay? And if you actually graph them, it's very weird, very unusual, not predictable. Again, I think I gave you the graph. Let me just, for those of you who came in late, let me just give you some graphs here. Yeah, look at this. Am I sharing this page?
Yes.
Am I sharing this page? Yes. I mean, these are some graphs, some equations which I typed in, especially this number 10 graph, has bunch of sine and cosine here. And look at this graph. What is this? Can you believe that this is a graph of an equation? Look at this. It's so weird out there. There's so many weird things out there. You know what? Whatever you can think of, it's out there. So as you can see. But even for these kind of graphs, the question is, are we interested in finding tangent lines? Yes, we are. But the thing is, we cannot solve for x in terms of y, or can it solve y in terms of x? You cannot do either one. And so x and y are completely mixed together, and you cannot even separate them, all right? So this equation, this is the kind of equation we're dealing with. Now, if you look at example number 9, it's a little bit better, but still, what is this? It kind of looks weird. And how about example 10? This kind of, kind of similar to example 10, but you know what? This has like 2 pieces. And if you look at the left-hand side, there's like a triangle island. And can you imagine that this is actually an equation? So what I'm trying to tell you is there are a lot of weird graphs out there. And of course, example number 12, this one is the r and theta. This is what we call the polar. It will be very complicated, okay? So anyway, this one, r equals 9 times 3 theta. When you go to top 2, you are to study these graphs. They're kind of nice. This is a basic flower with 3 leaves. And if you change that 3 into a 5, you get 5 leaves and 7 leaves or whatever. If you put a 4 there, I think we get 8 leaves. Yeah, that's right. If you plug in 4 in there instead of 3, then we get 8 leaves there. So there is a relation. So that number is not necessarily the number of leaves, but it is kind of related. But if that number is a prime number like 7, then we do get 7 leaves, and we can make an adjust. If you instead of 9, if I
there's kind of like a small museum that's nearby
out there, which are kind of weird, but there are also a lot of graphs which are nice. Okay, very nice. So, for example, let's say number 13. Number 13, yes. X of how about this? X. Maybe this is a graph of a square candy. The square candy is what? How about if I give, let's say, 4 power? The plus. Why it's the 4 power?
Yeah, I mean,
wait, did I tell you the candy equation?
It's 30 minutes. And then I have a call at 1, and then
equal to, how about 1? Make it bigger, let's make it 10. Like this. See? Look at this. This is what I call the candy equation. Why do I call this the candy equation? A square candy equation, because it's almost a square, but then the corners are rounded. Why? Because if you actually look at a candy, more square candies, the corners are rounded. And that's because we don't want to cut anybody, so cut anybody's mouth. So when the kids eat the candy, obviously they don't want to have a sharp edge at the end. So that's kind of dangerous, right? So make it a corner. And so depending on how round we want this to be, if you raise that 4 to a 6 or 8, then the corner becomes sharper. So if you make this into 40, then you can see 0, and then oops, almost a square. Oh, that's good. There's 0 here. Look at that. Oh, now it's almost a square. So see, I mean, when you look at this, it kind of looks like a square, but is this really a square? Well, if you magnify this, you will see it's not really a square. So now you begin to see that the corners are rounded here, and the lines, which are horizontal and vertical, it kind of looks like they are straight, but if you magnify this, you will see that they're not exactly a square. Okay? It's kind of curved, okay? But anyway, you can see that. So what I'm trying to say is there are a lot of curves out there, which are very weird. So if you think that all the graphs are like polynomials or like parabolas, so on like that, you know that you're wrong, okay? Those are only the easiest kind. Again, once we include these trig and exponential and you know other functions like this, there are a lot of weird graphs out there. So the point is, for even with all those weird graphs, are we still interested in finding the tangent lines? And the answer is yes. We are still interested in finding the tangent lines. So that's the topic of section 2 and 6. So you can graph example on ABC, and then you'll see that they're very ugly. Okay, all kinds of interesting weird graphs. We have all kinds of graphs out there. So whatever we can think of is out there. Okay, so now let's look at example 2. We are now going to study pieces first, and then we are going to put together into an equation like this. Ultimately, we'll get into like example 5, example 6, and example 7. That's what we're up to. So on this page, you have 3 problems here, example 5 and 6 and 7. And as you can see, can we separate the y? Can you solve for y in terms of x? And actually, for example 5, we can. But we can't solve for y in terms of x, but because that's actually a circle. And can you solve for y in terms of x? And yes, we can. But
it's watery. There's no flavor.
But you know, but we'll see. Okay, so that's the whole topic of this. Okay, excuse me. Just give me a minute. Okay, give me something happened here. So just give me a minute. I'll be back in a minute. Okay, excuse me, I'm active. Okay, so now what I'd like to do is, let's start from example 2. Example 2, part A and B. Now, when you look at these 2 examples here, example 2 is actually chain rule. But if you look at example 2A is chain rule. But if you look when you look at example 2, part B, this is what we call implicit differentiation. So what is implicit differentiation? It's really a variation of chain rule. It is chain rule in a sense, okay? So now let's look at example 2. What is that? That's a derivative of, okay, so let me zoom this and let me magnify this here. And let me clear the screen out. And so we have this. Okay, example 2. So that is the derivative of x squared. By the way, start from section 2.6, when it comes to implicit differentiation, we want to write dy dx and not as y prime. So once again, if you write the derivative as y prime usually means dy dx. Usually this is what it means. Okay? So when you say y prime, this y prime means the y prime of x. Sometimes we write like this. So we just write the independent of x right here. So same as like, so f prime of x. So when you have f prime of x, what is f prime of x? F prime of x is the derivative of f of x. So this is d dx of f of x. So in this case, we have to show our independent variable. So we have to show with what variable we are taking the derivative. So now we have to show this guy. When we had like y equals f of x, then we didn't have to show this. But starting from this, but in this section, in implicit differentiation, we now have to specify with what variable we take the derivative. Because, as you can see in example 3, we can take the derivative with respect to x. But you can take the derivative of the same guy, x squared y, with respect to dy. Or we can take the derivative with respect to t. Well, in this case, of course, we assume that x equals a function of t. So in this case, in example 3, assume what? In this case, assume what is it? What are we assuming? Assume what? Assume what? X equals x of t, and we assume that y is also a function of t, like this. Okay, but because we are taking the derivative with respect to different variables, we now have to specify. So this prime notation is not clear. So once again, when you write this and then use prime here, well, the question is this prime notation ddx or ddy? So that is the prime notation is concise, but this will be now unclear. This is dx, and that will be a question mark. So here we have parentheses here. Again, prime notation is therefore not clear. Prime notation is not clear. But on every specific problem, you can kind of say that prime means ddx, or prime means ddy, or prime means ddt, or any other variable like prime. Prime could mean ddz, or ddk, or ddc, dda. It could be any letter. And so as long as you, as long as you define what the prime notation is, then it can be used. But generally, on implicit differentiation and the related rates, I recommend you not to use a prime notation. If you don't know what's going on, then prime notation is just potentially confusing. And therefore, now the prime notation, because we can take the variable with any other variable, now we have a choice. That's why the prime notation will not be there. Again, up to section 2.5, there was only one independent variable, and that was usually x. And so because that was usually x, or yes, I did write some function with a t or something, but there's only one independent variable. So because there's only one independent variable, we take the derivative with that variable. It was fairly clear, okay? But now, not anymore. Okay, so now let's look at example 2, part A. What is the derivative of x squared minus 1 raised to the fifth power? And that will be, first, this is something to the fifth power. So the fifth power, x to the fifth power, the derivative is 5 times that to the fifth power, that to the fourth power. And then if the function is x to the fifth power, the derivative of x to the fifth power with respect to x is 5x fourth. But in this case, it's not really x. It's actually x squared, and then minus 1. So now that which we treated like a single letter, which is x squared minus 1, now we multiply by the derivative of that, which is now 2x.
This is really cool.
So this is now the final answer. Well, now why don't we just simplify this? Let me just, why don't I simplify this here? And if we simplify this, what do we get? Let me just write this down. Simplify this, we get equals 10x, and you get 10x and then times what? X squared minus 1, and then raised to the 10th power. So let me just put in the right component here. X squared, and then raised to the 4th power. So this is now the final answer to example 2A. Now let's say example 2B, let's see what we have. Now this is derivative of y to the fifth power. but this is not the derivative of y to the fifth power with respect to y, but this is y to the fifth power, taking the derivative of this y to the fifth power with respect to x, not y. So what we do is we keep the derivative of y to the fifth power here, and then we put the d there, but then d of y to the fifth power over dx is over here. So if we treat like a fraction, then we can put in a dy and a dy. And so this part right here is chain rule. Is that chain rule? Yeah, that is chain rule. That is exactly what chain rule is. If you look at this, see? So putting a dy there, that's what we call the chain rule. It is chain rule. But overall, this procedure is called implicit differentiation. So what is implicit differentiation? It is chain rule. Really, there's not much distinction. So now we put a dy there. Now what is the derivative of y to the fifth power with respect to y? Now that right there is the same as the derivative of x to the fifth power, and then taking the derivative of x to the fifth power with respect to x. And if we do that, that will be what? That is equal to 5x squared. 5x, 5, so 4 power, not 4, this. So this is it. Now, when you see these kind of formulas here, I want you to understand what this thing really means. Again, this equation is not really about x. When you see the letter x, all you have to do is you have to understand that these x's mean the same thing. So let me now mark with a mark with a different color. Maybe I'll mark this in green. So let me call this guy what? Let me block this off. Then maybe put a parenthesis around the green. Then maybe put around the x, and then around this x as well. So basically, when you see the x there, what does it exactly mean? It does not mean that there must be an x in there. All it means that these x's, they must match. So instead of x, we can have y, we can have 2x, we can even have sine x, we can have x plus y, we can even have yz, we can have anything in there as long as they match. Is that clear? So I want you to understand these formulas here. So you might say, oh, isn't that just the derivative of x to the fifth power? Yes, it is. But if these x's are something which are matching, then this is correct. So if you look at this example, if you look at this guy right here, yeah, we have a match here. We have this x right here, this x, and this x matching. And then once you have that, then the answer will be this right here. So now, what is that first part? The first term is now 5 what? It's 5y to the 4th power. That's what that is. And then now, what is dy dx? Well, on this part, dy dx is just left as dy dx because y is not specified. We don't know what dy is. So y is not given here. So we just write that as dy dx. And then, of course, this is not the end. Actually, this is the end. For example, 2b, this is the end. Because we don't know what dy is in terms. We do assume that y is written in terms of x, but again, y is not specified, and therefore we just keep it like this. So if you compare this example 2b to example 2a, they're actually very similar. If we let y to be x squared minus 1, then they're actually exactly the same thing. Whereas in example 2b, we just wrote it as y. In example 2a, we're letting y to be x squared minus 1. So example 2a is actually a special case of part B. Again, example part A is a special case of part B. That's all it is. Besides that, they're exactly the same. It is exactly the same. Now, let me go back to example 2a again. Let me now show you how example 2 can be done in a different way. And so to do that, what I'm going to do is I'm going to now, let me see. Let me erase this part right here. Okay, so let me, I don't want to erase that part. So let me just erase this part. Oops. Oh, I don't want to erase that part. So let me erase this part and this part right here. Okay, so now let's look at this one more time. It's example 2a again. Let's see. So what I'm going to write is example 2a. Example 2a. Okay. This is what? Notation 2. No, the notation 2, that means a different notation. And notation 2, different notation. It's essentially the same thing. But the only difference is actually the way we write it. And so we can write it this way. Now, this may look very weird or messy, but this is another way. This is the way many of you will be writing for those of you who will be going into more advanced math. Okay, so again, it's nothing new. I already mentioned this, but now let's see what we have here. So the problem we have is this: ddx of what? ddx of x squared minus 1, x squared minus 1 to the fifth power. So this is what we have, right? So this is x squared 1 to the fifth power, and then this, and then let me put a square parenthesis right here, square parenthesis right here. So now what is this? This can be written as the d of x squared minus 5, d of x squared minus 1 to the fifth power. So I'm going to write x squared minus 1, this whole thing to the fifth power. And then what? And then times dx. So we are to push this dx aside. And now why don't we apply chain rule? Again, this dx and dy, this is not dy over dx. This guy is not really a fraction, but it behaves like a fraction. So hence we write the derivative in a fraction form. Again, we write dy over dx like a fraction, even though it's not exactly a fraction, but it kind of behaves like a fraction. That's the reason why. So it is a fraction, not exactly, but it's actually, as you actually have seen before, it is actually the limit of a difference quotient. It's like delta y over delta x. It's like and then we take the limit. So it's just actually a limit of a fraction, so which is not exactly a fraction, but certainly behaves like a fraction. That's why we have chain rule, and we have all those rules which I mentioned last time. And so now what do? We now put this in. So now what we want to do is, how about if I write this in black? D of what? D of x squared minus 1. And it looks messy, doesn't it? This is x squared minus 1. And this one, let's put d of x squared minus 1. So once again, this guy is chain rule. This guy's chain rule. So when you actually, when you actually take the derivative of this guy here, when you apply chain rule, you can actually let this x squared minus 1 be w. Then you have dw, anyway, you can write it like this. Now this is another way to write. Now when you look at this, this may look very messy, complicated, but now let me ask you, what is this guy here? Do we know this guy? Do you know this guy? This guy, do we know? Do you know this guy right here? What is the derivative of x squared minus 1 to the fifth power with respect to x squared minus 1? What is that? Oh, that guy over there is actually the same as this guy over here. The formula which I wrote down above. That is the power rule with exponent 5. So the derivative of x to the fifth power with respect to x is 5x to the fourth power. And note that this x and that x is matching. Well, except in our case, we don't have x, we don't have x there. We have x squared minus 1 instead. So instead of x, we have x minus 1. But other than that, they look alike. At least this guy here, and this guy right here, this x right here, this x guy here, and this x guy, they match. So here, we are not, this equation is not about x. It's not about y. Whenever you see an x, then what you have to understand is, all it means is, mathematically, all it means that all these x's, they're matching, that's all. If you have an equation where there's only one x and there's no other x, then that means x can be anything. But as soon as you see two x's in some places, that means that the x's must match. They must be matching. They represent the same function or same number. That's what it means. It's not about x. So you have to understand what these equations mean. And so as long as we have those three things match, then this equation will fit. So this guy here, even though it looks terribly messy, yes. When students look at this guy, the students are very happy, right? When students look at this guy, then what is the student's reaction? The students are very happy. they're like this. But then when students see this guy, what happens? They are very sad, even though they're exactly the same guy. So here, what is it? They are sad. Okay? The sad face. Get that? So what I'm saying is that this box right here, the box in red, and the box in red on top and the bottom, they are really the same guy. The same guy. It looks different, and especially the bottom one, this looks much more complicated than the top one, right? But then what is that? That's the exact same guy. So this is equal to what? That is equal to, what is equal to what? Equal to 5 times x squared minus 5 times x squared minus 1 to the 5th power. X squared minus 1 to the 4th power. Now, note that this guy right here, which I boxed in red in the bottom, that is not chain rule. Again, let me tell you this. This guy right here, boxed in red, this guy right here, this guy right here becoming 5 times x squared minus 1 to the 4th power. This is not chain rule. Do you understand me here? Going from here to here is not chain rule. This is just the derivative of x to the 5th power with respect to x. Is that clear? So don't make a mistake here. This is not chain rule. This is not chain rule here. This is just a regular derivative. It looks much more messy, so that's why this kind of throws off many students. So you need to have very careful eyes here. Where the question is, do they match? Do they not match? What is it? Okay? And then now times what is the second factor there? The second factor, the derivative of x squared minus 1 with respect to x, and that is simply 2x. So that will be what? That is equal to 2x. So times 2x. And then what is it? And that's exactly what it is. And that is the final answer right there. So that's what we got. So that's it's not a different solution. I just wrote it differently. Instead of y, I just wrote x squared minus 1, and I did not introduce y anywhere. So advantage of doing it this way is what? You don't have any intermediate variable. You don't have y. Here, in solution 2a, the first solution, actually, you can create a y, but you don't have to. Anyway, I think that should be clear. But the second one writing, this will become more and more common for those of you who will be taking more math, especially when it comes to chapter 4. I will be using this notation. Why? Because if I use this notation, it will be easier than introducing another variable, intermediate variable. Any questions here? So key is to understand example 2a and b very carefully. And make sure that you understand in all different notations. Is that clear? So don't just get used to one way. Get used to many different ways so you have complete flexibility. You should be able to understand this way, all kinds of notations. I think there are about 3 different ways of writing it, but make sure that you understand all notations. Okay, when someone else writes, then you have to understand what they write. When you write, then I'm going to understand what you write. When I write, you have to understand what I write. So we have to understand each other's writing. And so these are different ways of writing. So whoever writes, they get to pick which way they want to write the solution. So your job is to understand all different notations here. Okay? Don't insist that I can do it this way. That's not the way to go. Okay? You have to understand what others write too. So you have to understand in all different notations. Any question? Example 2a and b. Okay. Anybody has? Can you hear me? Are you all there?
Yes.
Okay. Any questions on example 2a or b? Okay. If you have no questions, now let's do a little bit more practice here. Let's look at example 3. Example 3, I'm going to save this and clear this. Now let's look at example 3. So let's see what we have. Example 3 is this. Example 3. So now we have d dx of x squared y. So what is this? So it looks like we have applied product rule. So here, I'm going to slow down a step. So this is equal to now, what is this equal to? this is now going to be d dx, the dx of x squared. So d dx of x squared. So this time here, I'm applying the product rule. So d dx of x squared, so that would be f prime, and then g times y. You see a plus, and then here I'm applying the product rule, and then this is going to be x squared times x squared times dy dx. So this is going to be what d dx of y. Again, d dx of y. So that's just a regular product rule. So now let's simplify this. What is that? What is the derivative of x with respect to x? And that is simply 2x. And then times y. And then plus x squared. And now the last factor there is d dx of y. The derivative of y with respect to x. Well, we don't know what dy is. Y is not specified, so we just write dy over dx. Oh, by the way, when I did example 2b, I didn't mention this, but just like in example 2b, we also have example 3a, we also have this dy dx. This dy dx, this is what I call the chain rule factor. Chain rule factor. And it's very important. So we are getting a bunch of these dy dx's at the end. So this is the last expression. The final answer to this problem is over here. This is now the final answer. Again, when you look at this final answer, there's a dy over dx in it. And of course, you need to put this dy dx is a must. If you skip this chain rule factor, which many students do, if you skip this factor, how many points off will that be? If you skip that dy dx there, that's only one mistake. Yeah, you might think that that's the one mistake, but that's a critical factor. It's like the main meal is missing. If that dy dx is missing, it's like the meat is missing in your burger. So you have a hamburger, and then you know what? The beef is missing. It's like a chicken burger, and then the chicken is missing. Or you order a chicken noodle, and the chicken is missing. That dy over dx is the key. That factor is a must. If you skip that dy dx, that'll be 50 points off right there. Okay, there's no mercy. And besides, after that, everything will be all jump. And it doesn't make sense. So that's why it is a critical factor. So you must have that dy dx. Again, that's called the chain rule factor. It is critical. So when I grade your problems on these kind of implicit differentiation, I actually look at the overall calculation, and then I look for that chain rule factor there. If I do not see the chain rule factor, then there's nothing for me to give you. Okay? So you might say, some of you might say, oh, that's a tiny mistake. I think I deserve more than that, more than so many points. But you know what? You're wrong. You don't get that many points. You get nothing. Okay? So chain rule factor, missing a chain rule factor is like missing the main meal. Okay? It's like missing the steak. Okay? It's not missing a vegetable. It's missing the steak, and it doesn't make any sense. So when you have this dy dx, and then you take the rule with respect to this, then we know that there must be a dy dx somewhere, and if you don't have a dy dx, then the whole thing's wrong. So now we are taking the derivative of this guy with respect to y. And so therefore, this b is different. You don't get the same answer. This example 3b is a different problem. We get a different answer. Okay, is that clear? So this here, how about this? How about if we do this in one step? If you apply the product rule and then the chain rule together, we take the derivative of x squared, which is going to be 2x, times dx dy. That's f prime, and then g. F prime g, so that is f prime, and then g. F prime g plus f, and then g prime. Now x squared times the derivative of y with respect to y, which is 1. So this is actually the final answer right there. except we can simplify this. This is equal to, you can write this as 2xy, 2xy, dx dy. Yep, we have dx dy, not dy dx. So do not make a mistake there. This guy is, the factor is, chain of factor dx dy. If you change that to dy dx, so that will be a penalty too. There's nothing much I can do. So here, in the, when it comes to implicit differentiation, you make a mistake on single letter, that will blow up the entire problem. Again, when it comes to these kind of implicit differentiation, you make a mistake of one letter, and that's it. The game is over. You've completely changed the problem. There's nothing for me to give you. All right?
We're good, thank you.
On a 20-point problem, I deserve more than
We're
3
good,
points.
thank you.
You know what? You don't deserve 3 points.
Oh, we don't need
Just
any,
you.
thank you.
Okay? So be very, very careful.
Yes.
1 p.m.
These problems, if
1
you do
p.m.
correctly, it doesn't take that much time. So the question is, can you go from there to there directly? If you can go from there to there directly, just do that in one step, and you don't have to give me that one step. Yeah. So in this case, for example, 3 part B, you can just give me 2 steps here, and that will suffice. But if you're not clear about this, then we will slow down 1 step, and so this is what we'll do. So we take the derivative, this is apply the product rule. So that will be d dy of x squared. d dy of x squared, f prime, that will be f prime g plus f, and then g prime. So that is equal to now d dy of y. If you slow down 1 step, this is what we get. Or we get this right here. So now when you simplify this, well, what do we get? Now we get everything is clear. And now note that dy is 1. The derivative of y, with respect to y, is 1. So I didn't bother to write the 1 there. And then x squared, that's going to be plus y. Now the only thing is this right here. And it looks like I need to write one more middle step here. So now what is this dy? So let me write dd. Okay, so dy. Yeah, you know what? Let me just write dy over here. So dy of x squared. What is dy of what is the dy of x squared? What is the derivative of x squared with respect to y? Here we apply the chain rule. So that is for the derivative of x squared and derivative of x squared. And now we have dy here. So what do? We push the dy to the side. And now, since we have x squared, we want to take the derivative of x squared with respect to x. So we now put dx here, and we put dx here. And what is this rule? Putting a dx there and dx there, what rule is this called? Putting a dx here, what rule is this? This is called a what rule? Class, what rule is this called? It's just the implicit differentiation rule? Yes or no? Putting a dx there and dx there, what is this rule called? It's just called the implicit differentiation rule? Yes or no? Class, anybody? Can you hear me?
Yes.
What rule is this called? Putting a dx there, what is this? What rule is this called? What rule? Class, what rule is this? What rule? What
I
rule
think
is
the
this?
Leibniz rule.
What? Leibniz rule? Leibniz? No. The Leibniz rule is not Leibniz rule. This is the Leibniz notation. The rule is not called the Leibniz rule. This rule is called what? It's called chain rule. Chain rule. All right? That was the topic of the last section. This is chain rule. Chain rule. So once again, this is chain rule. This whole process is called implicit differentiation, but it's really chain rule. The implicit differentiation is just a variation of chain rule. Actually, it is chain rule. It kind of looks a little bit different. Okay, that's all. But it's really the same thing. So now we have that, and so now what is the dx squared of dx? That is the derivative of x squared with respect to x. So that becomes 2x. So that's why it's 2x right there. And then that's that. And then at the end, what is it? dy, dy of y. What is the derivative of y with respect to y? That is 1. And so I didn't even bother to write the 1 there. And so we just let x squared. And so the final answer is this guy right here. And of course, example 3, part B is not the same as part A. So they are different. Different problems, different answers. They're kind of related. Yeah, they're kind of related there. But yeah, they kind of, so something looks similar, but they're not the same. Okay, all right? If you multiply this whole thing by dy over dx, so dx over dy, then you actually get this guy. So there is actually a relationship between this one and that one, but you know what? You don't have to know that. But again, from part A, if you multiply that whole thing by dx over dy, that is dx dy over dx, dx over dy, then we actually get the answer to part B. Okay? So there is a much more closer relation than what you think, but for now, you have to know that, so I'm not going to bother. Okay? So anyway, that's that. So that's that. So now let's look at example 3, part C. Well, now what is ddx ddt of x squared y? So this is going to be now, take the derivative of x squared with respect to t. So this time what I'm going to do is, I'm going to skip the middle step here. So this is going to be what? This is going to be, should I just skip the middle step here? Or should I write the full step? Okay, let me just write the answer, okay? So this is going to be 2x. So product rule, 2x dx dt. So we need the chain rule factor. 2x dx dt. So that is the derivative of x squared with respect to t. So 2x dx dt, and then times y. Plus x squared times the derivative of y with respect to t. So we end up getting dy dt. And then basically that is it. This is now the derivative of, so that's the answer to what? 3, part C. If you want to slow down one step, just like part A and part B, you can. But at the end, that's what the answer. Of course, you know what? I think we can simplify this. We usually write the y in front of the dx dy. All the derivatives we tend to put at the end. So the first term, if you simplify this, we would just write this as 2xy dx dt, and the plus x squared dy dt. So that's how it goes. And of course, in the part C, if we know what x is in terms of t, if it's specified, then we can get that. Okay. Okay. So now let's do one more practice here. Let's look at example 4, part A, B, C. Okay. Now things are a little bit more complicated. Now, what do you think? Do you think we should do I don't think we should do all 3 of them. They're very similar, right? So which one should I do? Should I just do part B? Is that okay with you? I'll just do one of them. Okay? I'll just do one of them. So which one should I do? Essentially, they're all very similar, but of course they all have different answers. They're not the same. Okay? But so I'll just do one of them. So should I do part B or should I do part C? What do you think? Or should I just skip it at all? Or at least should I do one? Okay, now let me do one. How about if I do example 4, part B? Let me do this one here. This, I'm going to slow down one step here. I'm going to do ddy, the ddy of x. So here I'm applying the product rule first. That's the leading rule because it is a product. The argument of the derivative is actually a product. X times and the sign of something. So it's this right here. So I'm applying the product rule. F, I'm going to call this guy F and this guy G. So this is like taking the derivative of F times G. So this F prime G. What is G? G is what? G is going to be this. I'm going to, let me just type this in. This is going to F times G. This is sine of, oops. Let me change the color. This is sine of x times square root of y. That. F prime g plus f, and then g prime. dy of what? dy of this. Sine of x squared y. So once again, let me just type this in. Sine of x times y, x times square root of y. And then, you have that. So that is going to be square root of y. Then we have a parenthesis here. It's actually this right here. Does everyone understand the first step? Here, the first step is look at the argument of the derivative. The function is a product. So the leading rule is the product rule. First, we start with the product rule. F plus f prime g plus fg prime. That's what that is. So now, what is this? Now, what is this here? What is the derivative of x with respect to y? Well, f is not specified in terms of y, so there's nothing we can do. So we just what? We just write what it is. So we just write dx dy.
Almost done.
And we usually write this dy dx at the end, but for now, why don't I just keep the order, and then at the end we'll switch the order. So this is dx dy times sine of x squared y. This is sine of x squared y. Okay, so far so good. The plus, and then now what is this x? X, we just keep it. And now we have to take the derivative of the sine of x squared y. And now what? You know what? I'm going to let's see. How do we do this now? Here, what I'm going to do is I'm now going to look at this part right here. And let's look at this part right here. This part right here. Let's look at this part. What is that? And then it should be over here. Okay, that goes right there. X times that. Okay, so x times that. You know what? X times that. Okay, but anyway, the box there. What is the box there? So the box there. So this box right here is equal to. Now we have to apply the sign. What is the derivative of sign? Oh yeah, we can apply. This is going to be d of sine of x. You know what? Yeah, this is going to be difficult here. I'm going to have to make it thinner. So this is going to be d of sine of xy. The sine of xy, x squared y. And then now, push that dy aside. What do you think I need to put in over here? Can somebody tell me what I should write here and there?
Wow. DuckDuckGo is totally different.
D sine of x y.
Like I knew it was, but it's
What?
ridiculously different.
What?
It
The
gives
rest,
you
what do I need to write?
the
You know, apply the
newest
chain of
order from newest to late to. It starts with the newest. It doesn't.
What
Like
should
when
go
I googled
into that parenthesis there?
Dr. McCullough.
Yeah.
Not one. I haven't seen one
What is it again? I think you said something. What was it?
mandate protest. It's all
Sine of x squared y.
defeat the mandates. Defeat the
No, we
mandates
don't want to
march.
put sine
Defeat
of
the
x squared
mandates
y.
march.
If you
When
do
you
that,
Google
then
it,
the
it
first
says
factor will become 1, and then the
anti-vax
second factor will be the ordinary problem.
march.
So
Is
we
that
don't want to
weird?
put the sine of x squared y. What we need to put is this. Here, look at this class. We have d of sine x. If you have a function sine x here, what do we want to put here? We want to take the derivative of this guy with respect to what, so that we get the cosine. This is the question you have to ask. So if you want to get cosine x here, what is that we need to put here? Can you tell me? Is that too easy? I think that is too easy. Sometimes students get confused when I write something too easy. What is it that we need to put here?
X.
That's right, we just need the x there. So now when you see the x here, what does that mean? That means it must match. So now we come back to the bottom here. What needs to go down into the red box? What needs to go into that red parentheses? What needs to go in there? The red parentheses right there, D of what? What needs to go in? Over here. What needs to go into that parentheses right there?
X squared.
What should go in? What?
X squared of y.
Right, x squared y should go in there. So that's why initially it kind of looks awkward and difficult, but that's what it is. So what goes in here must be x squared of y. And then x squared of y. Get this. And now we have to apply this product rule again. So this is going to be cosine of, this is going to be cosine of x squared of y. And now, what is now times now the derivative? What is now the derivative of x squared of y with respect to y? So that will be dx. Let me put it over here. So that will be dx over dy. F prime g times that is square of y. F prime g plus f e prime. Now the derivative of square root of y with respect to y. So that will be 1 over 2 square root of y. And this guy right here, that is now this big parenthesis right here. And that should go in right there. Let me put a line here. They're not connected. All right? It's not equal to next line. That is not related here. So this box right here must go in right there. And then there is the final answer. Now, how many steps you have to do this, that depends on you. But on test, as long as you're reasonable, I will accept that. So just skipping one step at a time is okay. But things have sense. So don't do this. Don't do the whole thing in one step. Well, can you do this whole thing in one step? Well, I guess you can. But you know what? My recommendation is don't skip too many steps. You have to demonstrate that you know what's going on. I do at least ask you to at least show me 2 steps. So anywhere between 2 steps to 5 steps will be okay. So you have to show me some steps. Again, don't skip everything. Okay, that will be marked incorrect. Okay, that's too risky. Okay, so don't skip all the steps.